Okay, so we're going to start with a new topic this week. In fact, we're going to start with a new set of modules that are somewhat different from the earlier modules that were presented to you. Earlier, we focused on circuit analysis. That's what we've been doing for the past 5 modules. With the introduction of the op-amp, which is already considered a standard circuit building block. So these next 3 modules is really going to be more an introduction to electronics for all of you. We're going to start with the diode, that's this week, and then you're going to go through the bipolar junction transistor, and then the field effect transistor. So that's going to be the program for the next 3 weeks. Okay. So let me bring up my presentation for today. Okay, so the diode is the first electronic circuit element that you're going to be studying. And this is what I hope to be able to cover today. First, we're going to take up diode characteristics. And then we're going to take up the piecewise linear diode models. And there are 3 models that I'm going to introduce to you: the ideal model, the constant voltage drop model, and the constant voltage drop with forward resistance model. Then we're going to go into diode circuit analysis. Okay, first single diode circuits, and then we're going to cover multiple diode circuits. Okay, so what are diodes? Diodes are circuit elements that supports current flow in only one direction. Okay. This is analogous to a one-way valve in a piping system. So this is your one-way valve. It has a ball and spring arrangement. No? Let's say water is flowing through the valve. Water can flow from left to right, but water cannot flow from right to left. And this is because of the ball and spring arrangement. Plumbers refer to this as a check valve. Plumbers here in the Philippines, no? They refer to this as a check valve. So this is analogous to the diode, no? Where the water is current, no? And the direction of flow is the direction of flow of the current. So this is the circuit symbol for a diode. There's an arrow that indicates the direction in which current flow is supported. So in this particular case, current flow is supported from left to right, and current flow is not supported from right to left. The left terminal of the diode, we call it the anode, and the right terminal of the diode, we call that the cathode. So you're going to see the terminals labeled A and K, anode and cathode. Where do these terms come from? This is historical because the first circuit element that supported current flow in only one direction before the vacuum tube, one terminal was called the cathode and the other terminal was called the anode. And this was carried over to the semiconductor diode. Okay, we're going to study the diode from a purely behavioral standpoint. Purely behavioral standpoint. What do I mean by that? We're not going to discuss the physics behind the operation of the diode. The physics behind the operation of the diode you're going to take up in EEE 131. We're just going to study how a diode behaves when you place the diode in a circuit. So there are many different types of diodes. If I rattle off the different types of diodes, you're going to get intimidated. Maybe some of them you are familiar with. For example, you know that for lighting right now, we use light-emitting diodes or LEDs. There are what you call rectifier diodes. There are Zener diodes. There are signal diodes, pin diodes. There are many, many kinds. This is a sampling of the different types of diodes you might see in actual electronic applications. Now, for this particular course, EEE 123, we will limit our coverage to what we call PN junction diodes. PN junction diodes. And these are fabricated using semiconducting material. Okay, you're going to learn later on that there are three types of material from electrical properties perspective. You have your insulator, you have your conductor, and you have your semiconductor. No? So diodes are fabricated using semiconductor material, and usually they are made from silicon. Silicon being what comprises maybe 99.9% of all semiconductor devices right now. So this is how a typical PN junction diode looks like. If you buy a diode from a store, a through-hole diode from a store like this is how it looks like. And if you take a look, there's a band, there's this band, and that band indicates the direction of current flow. This band is actually the position of the anode, of the cathode. No? Itong band na to. In other words, going back to this, yung band nandito sa cathode. Okay, so some of you may already have had exposure to diodes in your laboratories. Let's discuss the characteristics of a diode. The characteristics of a diode can be described by what we call its characteristic curve. But before we get into that, I'd like to show you the convention for voltage polarity versus current direction for a semiconductor diode. So if this is the anode and this is the cathode, the standard polarity we assign for the voltage across the diode would have the anode positive with respect to the cathode. So take a look, no? Plus is on the left, minus is on the right. And the direction of flow, the positive direction of flow, is considered to be the direction from anode to cathode. So I sub D from left to right. So this is convention. This is convention, no? For voltage polarity and current direction. Okay, what is the diode characteristic curve? The diode characteristic curve is a plot of diode current versus diode voltage. So it's a plot of the diode current, I sub D, versus the diode voltage. And this is what the characteristic curve of a real diode looks like. We have two operating regions. We call it the forward bias region and the reverse bias region. Okay. In the forward bias region, there's a particular voltage beyond which all of a sudden your current exponentially increases. So the current is going to be practically zero, and at a certain point, your current will start to increase and it will exponentially increase. Now, in the forward bias region, we call the current your forward current. Okay. Now, the reverse bias region is when the voltage across your diode is negative. So this is our origin. So for all points left of origin, your voltage is negative. That is what you call the reverse biased region. Okay. In which case, your anode is negative with respect to your cathode. And in this region, you practically have zero current. You practically have zero current. You actually will have a very, very small amount of current. We call it a leakage current. But if you consider the value of the leakage current for silicon diodes, this is in the range of nanoamperes or 10 to the minus 9 amperes. That is how small your leakage current is. So for all practical purposes, you might consider the current to be equal to zero. So that is your reverse bias region. So this graph is not actually drawn to scale. The leakage current here is actually exaggerated. So I showed it not exactly at the horizontal axis, just to show you that there is that small amount of current, but that's actually exaggerated. If you take a look at the actual characteristic curve drawn to scale, this line is practically flat all the way. So those are your diode characteristic curves. Okay, There's another way of describing the regions of operation of a diode, and that is, this is what we call its conducting state, and this is what we call its non-conducting state. So again, no, we're talking about two ways of describing its region of operation. One is forward biased and reverse biased. And what differentiates forward biased and reverse biased is that, no, when we say it's forward biased, that means V sub D is greater than 0. No? And when we say it's reverse biased, no, this is V sub D is less than 0. Sorry, So forward bias, V sub D is greater than 0, and reverse bias, V sub D is less than 0. Now, when we say conducting state, iba naman yung criteria natin. No? In conducting state, we say I sub D is greater than 0. And in the non-conducting state, we say I sub D is approximately equal to 0. Okay, so those two are different. No? They should not be used interchangeably. Of particular interest, let me erase my annotation. Of particular interest to us is a voltage which we call V sub F. This V sub F we call the forward voltage. This is the voltage beyond which all of a sudden the current exponentially increases. Your forward voltage. And that forward voltage, the value of this V sub F is approximately equal to 0.7 volts for silicon diodes. For other types of diodes, it will be different. For example, germanium, another type of diode, which was very popular in the early days of semiconductors, V sub F is about 0.2 volts. And there are still other types of diodes. If you take a look at this characteristic curve, it cannot be described by a linear equation. Take a look at this curve, it cannot be described by a linear equation. When we say linear equation, we mean either a straight line equation or a linear differential equation. Thus, we call a diode a nonlinear device. A diode is a nonlinear device. A circuit that contains a diode is a nonlinear circuit. So what are the repercussions of a circuit being a nonlinear circuit? The rules for linear circuits will not apply. For example, superposition. Superposition only works for linear circuits. So if you have a diode circuit, which is a nonlinear circuit, you cannot use the principle of superposition. So just take note, no? The diode is a nonlinear device. If it is a nonlinear device, it is relatively difficult to analyze the circuit because our equations are going to be difficult to solve. So what do? No? We can model the diode using piecewise linear models. Piecewise linear models. That is, different segments of the diode characteristic curve are represented by linear elements. And there are three models which I'm going to introduce to you. The first is the ideal model, or the ideal diode model. The second is the constant voltage drop model. And the third is the constant voltage drop with forward resistance model. So let's take these up one by one. Let's start with the ideal diode model. So our starting point are the actual characteristics. What is our ideal diode model? Our ideal diode model has these characteristics. So note, the blue curve is the actual, the red is the model that we use. Okay, so what is this model that we're using? First of all, we call it piecewise linear because there are two linear segments. No, this is one linear segment, and then this is another linear segment. That is the model that we're using. When the diode is forward biased meaning the applied voltage the voltage that you apply across the diode tends to be positive. Okay, then we say that the diode is equivalent to a short circuit. Okay, so this is our diode circuit element. No, when it is forward biased, this is its equivalent circuit. It's equivalent to a short circuit. And what are the characteristics of a short circuit? The voltage across the diode will be equal to 0. So if you take a look here, this vertical line, the voltage is equal to 0. On the other hand, when the diode is reverse biased, okay, when is it reverse biased? When the applied voltage tends to be negative or is negative, then it is equivalent to an open circuit. So this is our diode circuit element. It is equivalent to this. And what is a characteristic of the open circuit? The current is equal to 0. So that is this line here. The current is equal to 0. So again, we break the diode up into two regions of operation, one forward biased, the other reverse biased. And for each region of operation, we have an equivalent circuit. In the forward bias, it's a short circuit. In the reverse bias, it's an open circuit. Now, when do we use the ideal model? We use the ideal model when V sub F is negligible compared to the applied voltages in the circuit. I'll give an example. No? For example, we're using the diode, for example, in circuits where the voltages are in the range of, let's say, 220 volts. 220 volts. If you consider V sub F for a silicon diode, that's 0.7 volts. 0.7 volts compared to 220 volts is negligible. Thus, it's justified to use the ideal model without losing much precision. So this is used when V sub F is negligible compared to the applied voltages in the circuit. Okay, what is the second model? No? So we took up the ideal model. The second model is what we call the constant voltage drop model. Again, our starting point is the actual characteristics. The model that we're going to use looks like this. That is the constant voltage drop model. You might think about it as the ideal model that you shift, okay? You shift to the right. Dati yung ideal model natin, nandito yung vertical line. Ngayon, we shift that vertical line to the right. So again, we have two regions of operation. But this time, our regions of operation are not going to be forward biased and reverse biased. This time, our regions of operation are going to be conducting and not conducting. So that's where the distinction between those come in, ano? So dito we say forward biased and reverse biased, no? But here we're going to say conducting and non-conducting. So when the diode is conducting, it's equivalent to a constant voltage drop. So if this is the diode circuit element and it is conducting, then it's just equivalent to a constant voltage drop. No? The voltage from A to K will be a constant voltage equal to V sub F, where V sub F is the forward voltage of the diode. On the other hand, when the diode is not conducting, it is equivalent to an open circuit. So the not conducting region will be from this point to the left. So from this point to the left, it is not conducting, it is equivalent to an open circuit. Okay. Now, when do we use the constant voltage drop model? So we use the constant voltage drop model when V of F is not negligible compared to the applied voltages in the circuit. So kanina dun sa example ko, using the ideal model, sabi ko, okay, if your applied voltages is 220 volts, 0.7 is negligible. Now, what if my applied voltage is 2 volts? Definitely 0.7 is not negligible. 0.7 is significant compared to 2 volts. And therefore, I should not use the ideal model. Instead, I can use the constant voltage drop model. Note that this is the most commonly used model. This is the most commonly used model, the constant voltage drop model. Okay, I already mentioned this, no? We no longer refer to the diode state as forward bias and reverse bias. It's now referred to as conducting and not conducting. Okay, our third model. This is the constant voltage drop with forward resistance model. Again, starting point are the actual characteristics. What will my model look like? Okay, this time I have a constant voltage drop. Okay, however, no, not constant voltage drop. I have a voltage drop. However, that voltage drop slightly increases, okay, as your current increases. So this line has a slight slope. And notice now that that red curve more closely approximates the blue curve. The red curve more closely approximates the blue curve. So now our line here has a slight slope. So again, we have two states, conducting and not conducting. The conducting state, the diode is equivalent to a constant voltage drop V of F in series with the resistance Rs of D, where Rs of D is the slope of this particular line, or is the reciprocal rather of the slope of this particular line. So that is your constant voltage drop model. When not conducting, it's equivalent to an open circuit. So not conducting would be from this point left, no? Where I of D is considered equal to 0. Okay, if you will notice, ang nag-iiba lang, dun sa tatlong models natin, ang nag-iiba lang are the conducting states. No? When you go to the non-conducting state for the three models that we studied, they're all equivalent to an open circuit. No? But the conducting state differs. No? In the first model, the conducting state is a short circuit. In the second model, the conducting state is a constant voltage drop. And in the third model, the conducting state is a constant voltage drop with series resistance. And we use this model when greater precision is required. When greater precision is required. But as I already mentioned earlier, most of the time we use the second model. Because if you take into consideration the difference in precision between the second and the third models, it's actually very little. Okay, are there any questions so far? Any questions? Any questions with respect to the diode? Its principle, no, that it supports current flow in only one direction, and that is the direction of the diode arrow. That it is a nonlinear element, but that we use piecewise linear models to model its behavior to make it easier to analyze diode circuits. Okay, how do we determine the state of a diode? And there are two methods. The first method, we start with the assumption that the diode is conducting. So we don't know, no? We don't know. Is it conducting or is it not conducting? So we start with the assumption that it is conducting. And we replace it with its model in the conducting state. Okay, what do we do after that? We determine the diode current, assuming positive direction of current is from anode to cathode. So that's consistent with this, no? Consistent with this with the convention, no? For current direction and voltage polarity. So we determine the diode current, assuming the positive direction of current is from anode to cathode. If the current ends up really being positive, then our starting assumption is valid and we are applying the correct model. And therefore, whatever we have computed is valid. On the other hand, if the current is negative, then our starting assumption is wrong. And the diode should have been modeled by an open circuit, no? Which is the diode model when it is not conducting. So this is one method of determining the state of the diode. So let's take an example. Okay. So this example, use the ideal diode model to determine the current I. Okay. So I have a 100-volt source connected to a 1 kilo ohm resistance. Then I have a diode and I want to determine the current I. I can start with the assumption that the diode is conducting. Start with the assumption that diode is conducting. So what do? I replace the diode with its model, no? With its model in the conducting state. And for the ideal diode model, that is a short circuit. So I will replace it with a short circuit. Okay. So this is now my 100 volts. This is my 1K. And my diode, I replace with a short circuit. So this is my anode and this is my cathode. What do I have to do? I compute for the current flowing from anode to cathode. No? So this is my I of D. And what is my I of D? I of D will be equal to 100 over 1K dahil short circuit to. Okay, which is 100 MA. Note, I of D is positive. I of D is positive. What does that mean? That means my current flows from anode to cathode. If I of D is negative, that means my current flows from cathode to anode. I of D is positive. Since I of D is positive, we know that our model is the correct model, right? Thus, we are using the correct model. And I will just be equal to I of D. Any questions with regard to this example? Very simple, no? Napakadali pa, no? Okay, note that 100 volts here is significantly larger than the forward voltage of silicon diode. So let's say this was a silicon diode. No? Let's say this was a silicon diode. Yung forward voltage ng silicon diode, which is 0.7 volts approximately, is very much smaller than 100 volts. if we had taken the forward voltage of the silicon diode into account, what would be the value of I? Can someone tell me? If we had taken the forward voltage of the silicon diode into account, what would be the value of I?
Try lang po. 0.993.
That's right. No? It would be 0.993 or 99.3 MA. No? 99.3 MA. So, you compare 100 to 99.3. Sabihin natin 99.3 yung tunay. No? Ang initial calculation natin was 100. What is our error? Okay. Our error is only 0.7. No? Sorry. Yeah. Our error is only 0.7. 0.7 MA. So the error is less than 1%. So for practical calculations, therefore, we really could have considered the diode to be ideal because we are getting very small error. Okay, so let's take an example where the voltage is smaller. It's 10 volts. So this time, let's use the constant voltage drop model. So kanina, no, we used the ideal diode model. This time, let's use the constant voltage drop model of the diode to determine I sub D. Okay, so we start with the assumption, we're using the method that we studied. No? You start with the assumption that the diode is conducting. Assume the diode is conducting. So you replace with its model in the conducting state. Now we are using the constant voltage drop model. So what is its model in the conducting state? It will be a constant voltage drop. So our equivalent circuit now is going to be 10 volts, 1K. It will be a constant voltage drop from anode to cathode of 0.7 volts, no? Because the diode that we are using is silicon. So what will be I sub D? I sub D will now be 10 minus 0.7 divided by 1K. Okay, and this is going to come out 9.3 MA. 9.3 MA. Okay, note that the answer is positive. The answer is positive. Okay, the answer is positive. What does that mean? No? That means that our current is really flowing from the anode to the cathode. The current is from A to K. And therefore, our diode is really conducting. It is really conducting. Thus, this is a valid equivalent circuit, and I sub D must be correct. I sub D must be correct. Are there any questions? Okay, what if is instead of 10 volts, this had been, let's say, 0.5 volts? What if that had been 0.5 volts? Again, no? We'll apply the same procedure. Assume diode is conducting. Replace with the appropriate model. So what will our equivalent circuit be? Our equivalent circuit, you'll have 0.5 volts, 1K. Okay, we assume the diode is conducting. So what do we have? We have a voltage source from anode to cathode of 0.7 volts. And then we compute for I sub d. Can someone tell me what will be the value of I sub d? What will be the value of I sub d? Anyone?
Sir?
Okay, I have an answer from Team C, negative 20 MA. How did you get that? Well, it's easy, 0.5 minus 0.7. So what is the voltage here at this node? Voltage here is 0.5. The voltage here is 0.7. 0.5 minus 0.7 divided by 1K. So 0.5 minus 0.7 is 0.2. 0.2 divided by 1K. Sorry, that's 0.2 MA, not 20 MA. Not 20 MA, Dito. Minus 0.2 MA. Okay, it's minus 0.2 MA. Okay, note that current is negative. What does that mean? If your current is negative, that means instead of flowing from anode to cathode, it is flowing from cathode to anode. The actual direction of current is from cathode to anode. But we know that the diode will not support current flow in that direction. The diode will only support current flow in the direction of the arrow. It won't support current flow in the opposite direction. Therefore, our model is not valid. If our model is not valid, what is the actual current? Anyone? What will be the actual current?
It would be 0 po.
That's right, because the diode will be equivalent to an open circuit. Okay. Okay, so that's how we use the first method. That's how we use the first method in determining whether a diode is conducting or not conducting. Again, what is this method? Let me just go back. You start with the assumption that the diode is conducting. You replace the diode with its model in the conducting state. Determine the diode current, assuming the positive direction of current is from anode to cathode. If the current is positive, our model is correct. If the current is negative, our model is wrong. Okay, so we did those two examples. This is the second method of determining the state of a diode. This time, we start with the assumption that the diode is not conducting, and we replace the diode with an open circuit. What do we do after that? We determine the open circuit voltage across the diode terminals, assuming the anode is positive with respect to the cathode. So, ang i-compute natin ngayon is V sub D, pero tatanggalin muna natin yung diode, We replace it with an open circuit or tatanggalin muna natin, then we get the voltage V sub D across the diode terminals, assuming A is positive with respect to K. If that voltage is less than the forward voltage, then our starting assumption is valid and we are applying the correct model. If that voltage is greater than the forward voltage, our starting assumption is not valid and the diode should be represented by its model in the conducting state. Now note, forward voltage, we only talked about a forward voltage in the second and in the third model. Actually, in the first model, in the ideal diode model, we can consider that to be the model where your forward voltage is equal to 0. Okay, so we can apply this rule to all three models, no? Where in the ideal model, your forward voltage is equal to 0. So let me use the example that I conjured up earlier. No, it's also my example here. So use the constant voltage drop model of the diode to determine I's of D, but this time let's use the second method. So what is our second method? We start with the assumption we start with the assumption that the diode is not conducting. And therefore we replace with an open circuit. So what will our equivalent circuit be? You'll have 0.5 volts. You have 1K. So now I have an open circuit here. This is my anode terminal. This is my cathode terminal. And what I have to determine now is the voltage across my diode terminals with the anode positive with respect to the cathode. Okay, what is V sub D equal to? Can someone just shout it out? Ano yung magiging value ng V sub D? Can I hear from you guys? Albert, ano magiging value ng V sub D?
Is it 0.5 din po?
Yeah, V sub D will be equal to 0.5 volts. No? Why? Dahil wala kang current, no? Open circuit, so wala kang current, therefore wala kang voltage drop dito. No? Kung wala kang voltage drop dito, that means the voltage at this point, assuming that the bottom is your reference, the voltage at this point will be equal to the voltage at this point, and therefore V sub D is 0.05. Okay, so what is the next step? No, is V sub D less than V sub F? No, so you compare V sub D to V sub F. Okay, if V sub D is less than V sub F, then the assumption is correct. No? Since we're using the constant voltage drop model, ang V sub F natin 0.7 because it is silicon, this is true. So this ends up being true. Therefore, my assumption is correct. So this is the proper model, and therefore what is I sub D? Then I sub D will just be equal to 0. Okay. So this is the second method of determining whether a diode is conducting or not conducting. So again, the first method, you start with the assumption that it is conducting. The second method, you start with the assumption that it is not conducting. But this time what you get is the open circuit voltage across the diode terminals. If it is less than your forward voltage, and that forward voltage will be 0 if it's an ideal diode model. If it is less than the forward voltage, then your assumption is correct. If it is greater than the forward voltage, then your assumption is wrong. So you have to use the appropriate model. Any questions? Any questions? What happens if we have multiple diodes in our circuit? What happens if we have multiple diodes in our circuit? Then what we have to do is we must test all possible combinations of conducting and non-conducting states of the diodes until we get a consistent set of states. Okay. We have to test all possible combinations of conducting and non-conducting states of the diodes until we get a consistent set of states. No? So ibig sabihin nun, for example, if I have two diodes, there will be four possibilities. Four possibilities, no? Two diodes, so they can be both conducting both not conducting, the first diode conducting, the second diode not conducting, and vice versa. 4 possibilities. So you have to test all 4, no? Until you get a state where the behavior of the 2 diodes are consistent with each other. There will only your circuit, no, your circuit, if it's just composed of diodes and resistors, can only exist in one state. So once you discover that state, then that's it. That's the state of your circuit. So the best way for me to explain the process is through an example. So here I have a 2 diode circuit. No? What I want to do is I want to determine the current I. So I assume that D1 and D2 are silicon with forward resistance of 10 ohms. So anong implication nito? Because there's a forward resistance that is specified, then that means we must use the third model. No? So this implies use of the third model. Kasi na-specify yung forward resistance. So I'm going to have 4 states, and these are my 4 states. I labeled it case 1, case 2, case 3, case 4. Okay. Where I say off if the diode is not conducting and on if the diode is conducting. What do I have to do? I have to test each particular combination. No. Where do I start? Let's start first with both diodes on. No? So ito yung una kong susubukan, itong case 4. Let's start with both diodes on. Now, why did I choose case 4 first? Actually, wala lang. No? I mean, no particular reason for choosing case 4 first. What you try to do is you try to make an educated guess. Based on the circuit, you try to make an educated guess of what the states of the diode are going to be. No? So I have a 15-volt source here. Okay. I have a 10-volt source here. So I'm making an educated guess that this 15-volt source will be enough to make this diode conduct and this diode conduct, no? Because, for example, for this particular diode, this 10 is also in the direction of the 15-volt, no? Making current go around this way. So it's really just an educated guess that I will choose case 4. But you can choose any particular case to start, no? So I choose case 4, both diodes on. So I'm going to use the first method, no? So I assume that both are on. So that means I have to use the first method. I replace both diodes with its corresponding model. I replace both diodes with its corresponding model. So what's my model for the diode in the third approximation or the third diode model? It's a constant voltage drop in series with a resistance. And that resistance is specified here, 10 ohms. No? So this is now my equivalent circuit for D1. And this is now my equivalent circuit for D2. Okay, can you follow so far? Nasusundan ba niyo? Okay. So what do I want to do next? No? Next, I want to compute for V's of X. Because what do I want to do? No? I want to compute for V's of X so I can get the value of I1 and I can get the value of I. If I know V's of X, I can do that. When all else fails, use the node voltage method. So we can compute for V's of X using the node voltage method. Okay. Actually, we only have 2 essential nodes here. So you only need 1 node voltage equation. And what is that equation going to be? Okay. You have this current plus this current plus this current is going to be equal to 0. No? So what is this current? This current is V's of X minus 15 divided by 1K. So that's this term. Okay. What is this current? No, pababa. That's V's of X minus 0.7 divided by 10 ohms. So that's this term. And then finally, what is this current to the right? Okay. You have V of X minus 0.7, minus 0.7. You have a voltage drop left to right, 0.7, plus 10. In effect, I'm combining the sources together. No? I'm combining the sources together. And that should be the voltage across the series combination of 500 ohms and 10 ohms. That should be the voltage across the series combination of 500 ohms or 10 ohms. No? Or another way of thinking about it is, since these are all in series, I can rearrange the elements. Itong 0.7 na to, pwede ko ilagay dito. So what will my node voltage be at this point? It's going to be 0.7 minus 10. So V of X minus 0.7 minus 10. Okay. So ito yung lalabas. Over 10 plus 500. Does everybody see how I was able to get this term? Can you just show me a sign that you understand how I was able to get this term? So that's still actually part of the first 5 modules, no? Nodal analysis. So that's equal to 0. So I compute for V of X. I'm going to get V of X is 0.648. 0.648 volts. Okay, so what's my next step now? No, my next step, I want to validate whether this is really conducting. And for me to validate that, you remember under the first method, I compute for the current, no, current of D1, which is I1, and I check whether that current is going to be positive or negative. In this particular case, since V of X is less than 0.7, I1 is going to be negative. No? As a matter of fact, I1 is going to be minus 5.16 MA. That's because the value of V of X that I computed is less than 0.7. So the actual current direction is not going to be from anode to cathode, but it's going to be from cathode to anode. So what does that mean about my assumption for D1? What does it mean? Clyde, ano ibig sabihin nun?
The assumption for D1 is wrong po.
That's right. That means my assumption for D1 is wrong. Since I already showed that my assumption for D1 is wrong, I don't have to proceed further. No, I don't even have to compute for this current anymore. No, alam ko na kaagad na yung case 4 hindi pwede. Yung case 4 natin, itong case na to hindi pwede. Okay. So what will I do? I have to try another combination. No? I have to try another combination. So dun sa previous combination na sinubukan ko, alam ko na yung D1 assumption is wrong. So let me just change my assumption. Let me assume that this is not conducting and that this is conducting. So that is case 2. D1 is off and D2 is on. So I now replace D1 and D2 with their corresponding models. Replace D1 and D2 with their corresponding models. Okay. So what do I have to do? Since I am assuming that this is conducting, I have to compute for the current flowing through the diode. No? And I have to show that that current is from anode to cathode to validate that it is conducting. No? So i-compute ko tong I na to. Fortunately, because D1 is an open circuit, what I have here is just a single loop circuit. This is just a single loop circuit now, dahil open circuit to. No? So it's actually very easy for me to compute for I. No? No? That's because I1 is equal to 0. So what is I? No? I can combine all the voltage sources I have in my single loop. So I have 3 voltage sources, 15 volts, that's positive, 0.7 volts is negative, and then itong 10 volts is also positive because I'm traversing clockwise, no? Traversing clockwise, so voltage rise positive, voltage drop negative. Okay. So this is now 15. The total voltage is 15 minus 0.7 plus 10 divided by the total resistance in my loop, which is 1K plus 10 ohms plus 500 ohms. I'm going to get 16.1 MA. Okay, note, I got a positive value. So anong ibig sabihin? I got a positive value. Ibig sabihin, mukhang tama yung assumption ko rito sa D2. Mukha, no? Mukha pa lang, no? Because I still have to validate the state of D1. So seeing that I is positive, the assumption that D2 is on appears correct. Okay. Ngayon, kanina na-test na natin yung state 4, no? So alam na natin na hindi ito pwedeng conducting while this is also conducting, no? We already know that, no? That because we tested state 4, we know that this cannot be conducting while this is conducting. So alam na natin na ito yung tama, no? But what if we had tested case 2 first? Ano kung ito yung unang test case natin? Then I actually still have to validate that itong diode na to is really off or is really not conducting. And how do I do that? No, this is now the second method, no, of determining whether diode is conducting or not conducting. We started with the assumption that this was open. So we have to compute for the open circuit voltage. And that open circuit voltage should be less than V sub F. It's easy for me to compute for this voltage. I just apply KVL, this particular path. Since I already know the value of I can get the voltage drop across my 1K. No? So using KVL, V1, this voltage is just 15 minus I, which we already computed, times 1K. And I'm going to get negative 1.09 volts. No? In other words, the voltage here is negative 1.09 volts. Note that this is less than V sub F. No? In fact, it is negative. It is negative. The fact that it is negative even forces it to be more reverse biased or more non-conducting. No? So since V1 is less than 0.7, that's less than V sub F, then the assumption for D1 is correct. No? We produced a consistent set of states. The set of states, D1 and D2 here, this off and this on, they are consistent with each other. They don't contradict each other. And therefore, this must be the state of the circuit. There's no need to test anymore case 1 and case 3. Alam na natin yung case 2 ang tamang state ng circuit. Any questions? Any questions with that example?
Dun po sa una, since alam na po nating hindi po pwedeng naka-on si P1, ibig sabihin po ba nun pwede na rin pong i-eliminate yung lahat ng case na naka-on si P1?
Hindi. I think I should be clearer, no? Ang sinabi natin is hindi pwedeng naka-on si D1 na naka-on din si D2. No? Kasi ang tinest natin was case 4, no? In case 4, we assume that they are both on, ano? And then when we assume that they're both on and then we replaced it with its models, nakita natin na yung D1 hindi pala pwedeng maging on. So the correct statement is hindi pwedeng naka-on si D1 na naka-on din si D2. So
Okay po. Thank you
So
po.
hindi ibig sabihin na laging magiging off si D1. Hindi ibig sabihin ganoon, ano. Alam lang natin na hindi pwede yung kombinasyon na yon. Okay, any other questions? Okay, so just to summarize, no, what did I want to achieve in this session? So you should be familiar with the piecewise linear models of the diode. Tatlo yun: ideal, constant voltage drop, at saka constant voltage drop with forward resistance or with diode resistance. You should know when each model is applicable. So ideal, pag malaki talaga yung mga voltages sa circuit, yung V's of F is negligible. Pag maliit yung mga voltages sa circuit, okay, then V's of F is not negligible. So use either the second or the third model. And then yung third model, it's actually not very often used. You use it only when you really want a lot of precision in your calculation. Okay. Then you have to be able to determine whether a diode is conducting or not conducting. And I showed you two methods for doing that. One, the starting assumption is it is conducting, and you replace the diode with its conducting model. And the second, the starting assumption that it is not conducting, and you replace it with an open circuit. So for the first, you have to determine the current and make sure the current flows from A to K. If it doesn't, then you know your model is wrong. For the second, you determine the open circuit voltage and make sure that that is less than V's of F. If it isn't, then you know that your assumption is wrong. No? Okay. So having said that, you now should be able to analyze at least DC circuits. No? Kasi ang mga circuits na examples natin so far, lahat DC. No? Lahat constant DC yung mga supply. Okay, so what are we going to do the next meeting? The next meeting, we're going to take up some very common diode circuits na not necessarily DC ang input natin. Ano? In fact, more often than not, AC. And so we're going to see how we analyze those circuits. So that's all I wanted to discuss for today. Again, no, if there are questions, I will stick around and answer any of the questions that you might have until the last person logs out of the session. Okay? So thank you.